Welcome to this explainer. Have you ever actually stopped and just thought about how that box of metal and silicon sitting right there on your desk actually understands what you're telling it to do? It's a completely fascinating question. And today, we are going on an incredible journey. We're going to descend all the way from the abstract, highly logical world of human thought and programming languages straight down into the literal, physical world of a processor.
Okay, let's dive into this. Seriously, how does a totally lifeless piece of silicon, literally just a sliver of purified sand, actually understand and execute our logical instructions? How on earth does it take a simple command like print hello world and actually turn that into glowing pixels on your screen? I mean, it feels like absolute magic, right? Well, today we are going to completely strip away that magic and look at the real core mystery of computation.
To do that, here's our roadmap for the explainer. First, we'll look at the human-machine gap. Then we'll get into translating our code, explore the processor's vocabulary, break down the fetch, decode, execute cycle. And finally, we'll reveal the illusion of magic. Let's kick things off with Section 1, the human-machine gap.
So when you write code, the computer actually has absolutely no idea what Python or Java or English even mean. It doesn't speak a language of concepts at all. It speaks a language of physics. And that secret language? It's binary. It only has two symbols, right? 0 and 1. But here's the thing. These aren't just random numbers floating on a screen. They represent actual, literal, physical states inside the computer. A 1 simply means a tiny electrical signal is turned on, and a 0 means it's turned off. That's it. Everything in our entire digital universe, from the complex code a programmer writes to that massive video game you're playing, it all must be broken down into millions and millions of these little on and off electrical switches.
Which brings us to Section 2. Translating our code. Now, you might be wondering, if our code starts out as just regular text, how does it make that massive leap into raw electrical signals? Well, we need translators, and there are two main types of programs that bridge this gap. First up, we've got compilers, which are used in languages like C++. Think of a compiler kind of like translating an entire book into another language before anyone even starts reading it. It does all that heavy lifting ahead of time, which, usually makes the final program run much, much faster. On the flip side, we have interpreters, which are used in languages like Python. An interpreter is actually more like having a live translator standing right by your side, literally translating your code one single line at a time as it runs. So it might be a bit slower, for sure, but it's often way easier for a human to just write and test things on the fly. But how does this translation actually mechanically happen? Well, it happens in steps. Imagine you're learning a brand new language from scratch. First, you'd probably try to just identify the basic nouns and verbs, right? That is exactly step 1, lexical analysis. This is where the source code is broken down into little chunks called tokens. Then, obviously, you try to figure out the grammar. Like, how do those nouns and verbs actually fit together? That's step 2, syntactic analysis, which builds something called an AST. And finally, the whole shebang is translated down into step 3, pure machine code. Now, what's really fascinating here is that concept of the abstract syntax tree, or AST for short. Basically, the parser takes those little vocabulary tokens from step 1 and fits them all together into this beautifully structured tree. It maps out the relationships between the tokens just to ensure they actually conform to the programming language's strict rules and grammar. It's kind of like sentence diagramming, but for code. So the absolutely crucial point to take away here is that an AST strips away all of our messy human formatting. All those extra parentheses, the random spaces, the line breaks, gone. It retains just the pure logical structure of what you're trying to do. It basically acts as an intermediary representation. I love this because it perfectly shows how the compiler truly grasps the underlying syntax of your code. It's double-checking that your instructions actually make logical sense before it even attempts to turn it into binary machine code. Okay, moving right along to Section 3, the processor's vocabulary. So once our code is finally translated, it heads straight to the quote-unquote brain of the computer, the CPU. Now, every single CPU has an instruction set architecture. Think of it as its fundamental vocabulary of commands. And honestly, you might be completely surprised by how incredibly basic it is. The CPU isn't some super brain with deep intuition. It's more like a super fast but very simple-minded servant. It can basically only do 3 things. First, simple math, like adding or subtracting numbers. Second, data movement, taking data from main memory and loading it into these ultra-fast little internal holding spots called registers, or, storing it back. And third, logic and control. This is stuff like comparing 2 numbers and jumping to a completely different instruction based on the results. And actually, that's really it. I want you to really notice the powerful contrast here. Just look at how one elegant, simple line of human logic, something like var result equals x plus y, completely explodes into a tedious, highly literal sequence of hardware commands. The CPU can't just do it. It has to explicitly load x into register 1, then load y into register 2, then add those two together and put that into register 3, and finally, store that resulting number back into memory. It's crazy. One high-level thought instantly becomes many hyper-specific physical actions. Let's dive deeper with Section 4, Fetch, Decode, Execute. This cycle right here is the continuous loop that drives literally everything inside the processor. It is the literal heartbeat of computation. I always like to think of this rhythm exactly like a chef working in a busy kitchen. Step 1 is fetch, that's grabbing the next instruction, or, the recipe, from memory. Step 2 is decode, where the control unit reads the binary and figures out what that recipe actually means. Step 3 is execute. The CPU performs the operation, which is like the chef actually firing up the stove and cooking the dish. And finally, step 4 is update or write back. This is saving the result and cleaning up the station, setting up for the very next dish. Now, obviously, if the CPU did this one tedious step at a time, like sequentially waiting for one entire instruction to finish completely before even starting the next one, it would waste a massive amount of time. So modern CPUs use this brilliant trick called pipelining. It acts exactly like a factory assembly line. So while one instruction is being executed, the next one is already being decoded, and a third one is actively being fetched. This overlaps the stages so beautifully that the processor's execution units almost never sit idle. It just vastly increases the speed of the entire cycle. And that perfectly sets us up for Section 5, the illusion of magic. So if a CPU is actually only doing one incredibly simple, tiny thing at any given microsecond, how on earth do we see 4K videos playing and massive 3D games rendering all at the exact same time? Well, it all comes down to absolutely staggering speed. A modern CPU repeats its core fetch, decode, execute cycle at a rate of roughly 5 gigahertz. To put that into perspective, that means the tiny little crystal oscillator inside the chip is generating 5 billion pulses every single second. 5 billion. Let's just drive home this physical reality for a second because this is wild. One single tick of a 5 gigahertz clock lasts just 0.2 nanoseconds. In that infinitesimally brief window of time, light itself, literally the fastest thing in the known universe, barely travels 10 centimeters. I mean, that is how unbelievably short the window for a single computational step truly is. It's almost hard to wrap your head around. And on top of that raw speed, we have some incredibly clever engineering tricks that enhance this whole illusion of multitasking magic. We've got multi-core processors, which, as you probably know, are literally multiple CPUs packed onto one chip, allowing for true parallel instruction streams. We have your computer's operating system performing what's called context switching. That's rapidly swapping tasks in and out of the CPU hundreds of times a second, so everything just feels completely simultaneous to us. And we also have SIMD, which allows the CPU to process large chunks of data, like multiple pixels of an image, all at once with just a single instruction. So what you should really take away from all this is just a profound appreciation for that little box sitting right there on your desk. Beneath all the elegant software, the beautifully designed apps, and the deeply complex human logic lies a cold, precise, and unbelievably fast system of tiny electrical switches. As the old saying goes, it's magic, but it's physics. No matter how complex the code gets, all roads eventually lead straight down to those precise, literal binary instructions. Okay, so we've just successfully decoded how computers understand perfectly structured, highly logical code. But that leaves us with an incredibly fascinating question for the modern AI era. Think about it. If computers only understand strict physical states of ones and zeros, how on earth does an AI make any sense of our messy, nuanced, and highly emotional human language? Well, we are going to be exploring that exact mystery in our next explainer.